Okay. So, what is an atomic operation? Okay, something that's either uninterruptible or completes in one, as if it happens in one CPU cycle, something along those lines. Not divisible, can't divide it up, so something like that. And then what's a semaphore and when would we use it?
Synchronization.
Okay. And when would we use it? And the correct answer can't be when synchronizing.
When there's a shared resource that you only want one process to have access to at a time, we're using semaphore because the increment and detriment operations are atomic. So
Okay. Close. What if we want to have 4 people to have access to it at once? Would a semaphore allow us to do that? Yeah, because of the increment and decrement, it's atomic. So we started off, it's a special purpose integer, effectively, right? That's what a semaphore is. It's an integer where the increment and decrement operators are atomic, right? So we started off at the number of resources that we have, or the number of people we want to give access to that resource or those resources, and then we decrement whenever we give access to it. We increment whenever somebody gives away access to it. Okay, so we use it to protect access to a resource.
What did you even download? Muhammad ISIS plans?
This stuff? Yeah, they're plans.
Okay.
Various. Those are my grad student papers. They put everything in zip format or RAR format or
God,
the 7Z. Have you seen that one?
I've seen
7-zip.
Oh.
That's the best. Nah, that's the worst. One more till you die.
When RAR till you die. Except they...
There's like one guy on the internet who does that. It was on accident.
So what did I just click on? I donated to what? Why did I leave my PayPal logged in? Did you see that Wikipedia is trying to get donations now?
They've been trying to do that for like 3 years. They just now have made it so like the whole page
Pops up, right? So it's so annoying to have to just hit the big X. I wonder what would happen actually though if Wikipedia implemented a subscription service where they only. How come every single class you look more and more beat up?
His girlfriend's rough on him.
Yeah, we had a tournament this weekend.
This is you had a tournament this weekend, and what, you just got your ass handed to you?
No, actually, I got second.
So the guy that got first whooped his ass.
You should see everyone else.
Did
you wear headgear?
Yeah.
Okay. Good.
So how does this? I thought like it's supposed to be like you're not supposed to have marks after.
No,
wrestling.
It's a brawl.
Yeah.
Sometimes they throw knives into the ring. It's really
No, you beat the crap out of each other the entire time.
It's like the old Thai fighting. He goes over and he dips his hands in glue and then in a shattered glass. What was I talking about? Huh? No, I was in the middle of something before I got distracted by that. Huh?
Wikipedia, if they.
Oh no, we were talking about Wikipedia.
Yeah.
If they actually did implement a subscription service where for free you could basically get like the article headings, and then you, huh?
Do you ever read more into the Wikipedia?
Well, I would say I do, but I read weird stuff on Wikipedia, like details of algorithms I haven't heard of and stuff like that.
Peterson solution.
The Peterson solution, of course. It's actually a hobby of mine. I go on there and I follow like the breadcrumbs to find some algorithm I've either never heard of or never implemented, and then I give it as a homework assignment in my grad class. That way I have the opportunity to solve it.
Why am I taking
Just dead serious. Just dead serious, I do.
Taking a grad class.
I mean, we're doing, let's see, last week in that class was bloom filters. That was a fun one. Actually, it was easier than it should have been. So bloom filters is a way of deterministically deciding whether something is probably in a data set or not. Let's say you have a list of 4 trillion things. So rather than applying a search algorithm to it to find out whether something's in there or not, you can find out if it's probably in there or probably not in there using some collection of hashing algorithms and stuff. So that was kind of a fun one, but not very difficult. This week we're doing LZW compression. It's kind of the starting algorithm for most of our modern compression algorithms. So it uses a dictionary. So who knows what's going to be next? I'm going to actually write a little algorithm, just goes through and follows random links on Wikipedia and basically generates a question. Implement this. And
What do you think would happen on the education side if Wikipedia was a
They would probably be
1,000 different Wikipedia sites.
probably that's true, but there would also be at least initially less copying and pasting directly from from Wikipedia. I think that's what happens too often in when I see from students is I don't care that much if you get your resources from online, get your words from online resources, but I would like to see you paraphrase it at least because that's kind of evidence that you read it and then put it in your own words. It's not so much that I want to see your words instead of Wikipedia's words. I want you to have read Wikipedia and processed it somehow and then kind of put it into your own words. And even if you don't change the words that much. But I think what happens more times than not is we see this in our grad classes is students copy and paste from stuff and they try to find ways of getting around the auto check thing in Blackboard. So they use like a thesaurus that goes through and it replaces words in there with.
Don't work well.
Okay. But what's funny is we see them thinking that they're like changing the names of like the author and stuff. So like if the author's name is something Waters, they'll change it to streaming. Stuff like that. It's pretty entertaining. It's amazing the amount of time students will spend to save time reading something. Where if they just read it and put it in their own words, it would probably take less time than they spend trying to cheat. I don't know. Very.
Don't read it and then make it up. It's even less work.
Well, at least you're using your imagination then. It's like, well, if I were doing this is probably how it would work. And realistically, I mean, when you think about how we do things here in class, more often than not, our suggested solution to something is fairly close to the actual solution. It kind of bumps us up against the 2 or 3 things that maybe we didn't consider in our first guess. But, if you, at least that's proof that you used your brain. It's like, well, I'm not going to look this up because it's not worth my time, but I voice dictated how I would solve it, and I presented that as the solution. And okay, you get an 80%. That's close enough. Better than copying from Wikipedia. All right, so we talked about semaphores. So their real power is in the atomic nature of their increment and decrement, right? That's the punchline for those guys. Otherwise, semaphores are super simple, which is why they're so popular when it comes to synchronizing a resource or putting a bouncer in front of a resource. I think the question came up last time is this something that happens often? Are we protecting resources often in our programs? And the reality is yes. Even inside of our normal applications. So if we kind of take this outside of operating systems, and a problem came up the other day on one of the projects I was working on, which kind of involves like a social media type thing. So let's take something like Facebook. When somebody likes a post, well, what if 5 people like that post at the same time? and the database doesn't get updated correctly. Maybe 3 of them take. The other 2 kind of got misfired or something like that. So we have to have some sort of mechanism, some sort of flow that queues up to collect those likes, so that only 1 like gets recorded at a time, but 5 million people could potentially like at the same time. Those just get handled on a first come, first served basis at some sort of synchronization level. So maybe there's a semaphore that protects the function that ultimately updates the database with the new like. And maybe that semaphore is set to 1, and fine, it's, you know, it doesn't take very long to update it, but at least we're guaranteeing only 1 process is updating that database at a time. Okay, so it decrements, makes an update, increments, and then somebody else can go into the special room for updating it and go into the function. Java has this built into it through, as does C#, through the synchronized keyword, which we've never introduced in class, unless you took 390. Oh, I think it was 2 years ago. I don't think any of you would have been in there. But in any case, the synchronized keyword is basically a way of guaranteeing only 1 thread has access to this function at once. So even if you have 10 threads that are off doing their own thing and they all try to call it, magically Java has created a queue where only 1 guy gets in there at a time, so they can't overwrite each other's work. So we might do that for controlling. I think the example we probably used last time, which is maybe the easiest example to duplicate, is changing a file. So the contents of a file. If 5 of us open up a file right now, and then take our time making changes to it, and then save it, whoever saved it last is going to be that's the new final version of that file. Makes sense? And we've seen it in some of our applications today that they are kind of aware of that issue, and sometimes they'll yell at us and say that the file on disk has changed from the current file you're working with. Do you want to bring your file up to date with that, or merge the differences, or that type of stuff? Okay, we talked about mutual exclusion last time too, didn't we? At least we have some of these operators called mutex, but mutual exclusion means 2 things happen independently of each other. So most things are we separate solutions into multiple pieces where we try to keep as much stuff separate that doesn't have anything to do with each other, and then only control the 1 resource that actually is shared, rather than putting a bouncer in front of the entire mansion when we're only actually trying to control access to 1 room. That make sense? Something along those lines. Whatever. Okay, so semaphore implementation with what? With busy waiting and without busy waiting. I probably referenced the observer design pattern last time with this guy. Did I do that? I feel like I probably would have. But you know, the idea is that if you're waiting on a resource, you could sit there, just keep checking, and that doesn't seem very efficient if there's other things that you could be working on. Okay, so the observer design pattern basically says it's a good idea to keep busy while you're waiting for some event to occur. In this case, the event being that a resource becomes available. All right, so rather than everybody lining up, for the bathroom, you kind of go off and do other things, and every 10 minutes you circle back by and see if the line's gone down or something like that. Funny story related to that. Christmas at Concordia. So I go to this thing, and so there's like this president's dinner for it's rich folk. So anyways, I get a free dinner out of this thing. And so I go, but I leave during the student speaker thing, because that way I can get to the bathroom before the crowd gets there. Because that's at the end, before they usher us into our special seating or whatever in the church dealy flippy. So I'm in there playing Hearthstone. like a half hour. And it didn't seem very noisy out there, but apparently the other thing I come out, there's a line of like 14 guys just waiting. Oh, it was. I mean, like the president was in line. Oh, huh?
She walked out, just don't go in there.
The worst part is all I did was pee.
You are. Why do you sit down to
Play video games. Durr.
You can go back in there and listen to the student speakers.
At least I didn't have the audio on. That would make it so much worse. Especially with Hearthstone sounds. Welcome.
Isn't there? Were you in the terrace room for that?
Yeah.
There's literally another bathroom the floor below?
Well, that's true, but a lot of people don't know that. That's the backup resource. So there would have been a less used semaphore down there, I'm sure. I wonder what would happen if some student kind of dressed up in like a suit and stuff and hung out in the bathrooms and was like handing out towelettes and things like that and had like a little tip plate, if they would start getting tips from people.
No. I think they would. Oh, I would.
For-
Just 'cause that'd be
maybe
too
for,
awkward. Like,
maybe for something like that, but like college kids, like, no.
By the way, if any of you are interested, I have an absolutely hilarious story related to that kind of situation at a fancy restaurant one time that is not appropriate for recording. But
Just pause the recording.
it's not even like right for class. But I promise you, it is absolutely hilarious. It would fall into one of my categories of there was an incident. And I had to, and we can relate it to operating systems by saying we had to bring external resources to help with said incident. All right. So in any case, ask me about that at another time if you're interested. Okay. So we have two different ways we can work with semaphores. I mean, the semaphore itself doesn't change. A semaphore is a semaphore. It's just an integer. It's not that complex. Atomic, increment, and decrement. But so now if we think about it from the process's perspective, the guy who needs access to that resource, how does he check on that semaphore? How often does he check on that semaphore to see if the resource is freed up? So, one thing is we don't necessarily guarantee the human version of fairness. We don't get that first come, first serve thing with semaphores because we have to have some sort of scheduling algorithm that governs the line. All right, so we can have all these processes literally just standing there in the line, twiddling their thumbs, doing nothing, or we can come up with some sort of, cadence to them where maybe they check back every random 2 to 10 milliseconds or something like that, because we want to maximize throughput to that resource. If you have a resource that everybody's waiting for, you don't want to have a whole lot of downtime where the resource isn't being used because the right people haven't checked in yet. Right, so we want to maximize the use of the resource, but we also want to maximize the productivity of those waiting for that resource, and that's where that mutual exclusion stuff comes in, where there are things that they could be working on that exclude the use of this resource, that aren't reliant on the use of this resource. And we want them to be able to go and work on it, but we also want them to make sure they come and get the resource when it's available, but not waste all their time checking to see if it's available. Another example of how operating systems are a bunch of guesswork, right? We're rolling dice. I mean, you could literally probably implement an operating system based on the D20 dice system and probably come out with a final solution that isn't far off or from a performance perspective to what we have right now. A process needs access to the resource. Semaphore says they can't go in. They roll a D8. Got a 3. That's how many milliseconds I'm going to check back. So, but then you have to deal with the efficiency of your random number generator. And, it's possible I lied about the performance thing, but it might not be perceptible by a human. That's I guess the deal there. Okay. So busy waiting versus non-busy waiting, there's not necessarily a right answer. Sometimes you have a resource that is not all problems can be subdivided into mutually exclusive parts. You know, sometimes they have to wait in the line until they can go on and do the next thing. Okay, if you click the button on your Facebook page to like something, yeah, you want the page to still be clicky and stuff like that, but from a human perspective, we have an expectation that the little, what is it, a thumbs up? Well, I don't know, what does it even look like on Facebook? I never pay attention. It's just almost a blur, right? You have an expectation that within a second or something like that, that the thumbs up that used to be grayed out is now lit up, right? So Facebook can do a couple of different things for that. They can either fake it, say, okay, you click this, we'll take care of it, and they light up the blue light. And if you really want to test how they implement it, what you could do is you can go back to the previous screen, then come back to the screen real quick, and see if you've had your turn on that. You know, if you're doing a thumbs up on your friend's birthday, chances are there wasn't a huge line for access to that particular data record. But if there's some big event, Super Bowl or something like that, where zillions of people are commenting on something or liking something, chances are you might be able to catch them off guard, where you see the interface update to fake you out when the actual work in this behind the scenes hasn't been done. Something like that. All right, so sometimes busy waiting is required, but we need to think about faking out the human beings. Just as everything else. Okay, so this is something we talked about before, but it's also something we need to consider when we're dealing with resources. So the resource we talked about before when we were talking about deadlock and starvation was the CPU. Now we're bringing all the other possible resources in the system into consideration. So even if we're using this Facebook likes scenario, you know, if we have some sort of scheduling algorithm, we have 10 million people who've all decided that they liked what I had for dinner last night. What did I have for dinner last night? Oh, leftover Chinese. It wasn't that impressive. Did you know egg rolls get really, really soggy? Especially if you put them in the container with the General Tso's chicken. Yeah, it was unimpressive, to say the least. But in any case, the idea might be that depending on the cadence that those folks who are waiting in line to like that randomly select. Maybe they all wait 2 milliseconds from when they go, or maybe they randomly select a number of milliseconds between 1 and 8 when they're going to check back. You know, depending on the randomization, depending on the roll of the dice, you might have some of those guys that effectively get starved out. They never actually get they never actually are able to grab the resource, because every single time they check back, it just happens to be in use. All right, so you know, that would be the idea of starvation, and we don't want that to happen. We want we want everybody to ultimately get access to the resource they need to get. But in this case, it's like, well, how do we do that? Do we have kind of a priority queue for these folks, where if they've been standing around for a while, this is kind of what we were talking about with CPUs, that maybe we bump them up the list, they get access next, that kind of thing. Similarly, we have this idea of deadlock. So deadlock, 2 or more processes are waiting indefinitely for an event that can be caused only by one of those processes finishing. Okay, so now this gets back to this idea of mutual exclusion. So let's just say that, well, we got the Diet Coke scenario again. Okay, so in order for let's see, can I come up with a real life scenario? We might not be able to. We might just have to make a fictitious scenario.
What about the McDonald's one? Somebody's preparing your food. Both waiting for it. Both trying to leave.
Okay, so we're both trying to leave. Both our orders are in. We're both trying to leave, but we can't leave until the order is done. But the problem there is that we wouldn't have deadlock, because eventually the cook would finish one of the orders, which would allow me to leave, which would then allow him to move on to the next order so that he could leave. Deadlock is really a situation where whatever I'm waiting for, he's also waiting for, and I can't progress until he's progressed, and he can't progress until I've progressed. So we're literally blocking each other from doing anything, because whatever problem we're working on are 2 coupled. They're too intertwined that we can't make progress because of the current state of the machine, something like that.
It's like one of those co-op games where one player has to wait for the other to do something.
Yes.
And then once he catches up and does everything, then he can keep moving.
But deadlock wouldn't be that. Deadlock would be a situation where one player is reliant on another player to do something, and that other player is reliant. He can't do that something until the first player does something else.
So they'll have to pull a lever or something.
Something like that. But they physically cannot do both things. Somehow they've gotten out of sync where one guy got past the trap door when the other guy, they both needed to go through at the same time. So they're kind of on the wrong side of it. And what actually needs to happen can't happen. All right, so now we need to have a way of recovering from deadlock. And sometimes the solution is suicide. You know, we kill off one of the processes and effectively restart it. So that he can reset his scenario and be able to catch back up, and then they can go through and do it properly, that type of thing. So, again, it's kind of the same thing we've been talking about. Okay, so, dining philosophers. I love this problem. Okay, so especially the dining part of it. So we have some classic synchronization problems. The bounded buffer, readers and writers problem, which I think I'm familiar with, but I don't remember it off the top of my head. Dining philosophers problem. This one's cool with where your forks are. We'll see this here in a few minutes, hopefully. Hopefully there's a picture. Maybe dinosaurs eating. Well, there's this really funny video my wife put up on Facebook the other day. That was, it was like a Christmas dinner thing, and the people at the table were mostly dogs, and there was one cat at the head of the table. These were real animals, and they had them wearing, like, you know, a hat and, you know, stuff like that. And it was the people's arms eating and stuff like that. Okay, well, so if you ever had a cat, cats are not going to just eat whatever. Dogs will eat whatever. So, you know, but the cat was kind of the head of the table, and, you know, like, kind of the arms went up and told everybody to start eating, and the dogs all had these different personalities, and it was actually quite funny. But then some of the dogs are going, because they were lifting up the forks, and the dogs would eat off the fork and stuff like that. And then some of the dogs would lean over to the person next to them and start eating off that fork. And yeah, I think I liked it on Facebook, so you might go and find that and watch it. It was pretty funny. Okay, so bounded buffer problem. So we have n buffers. Each of these guys can hold one item. Okay, so we have a semaphore initialized to the value of 1. Okay, so we're controlling one resource. So we actually have 3 semaphores. So we have one semaphore called mutex, mutual exclusion. That's 1. We have another semaphore called full, which is initialized to 0. And then we have another semaphore, empty, which is initialized to the value n, which is the number of buffers that we have. So this guy is controlling the number of buffers we have, but because of his name, it's whether or not those buffers have been emptied. All right, how many buffers actually have something in them that can be used? Full is going to move in the other direction from empty, and then mutual exclusion is mutex is going to protect an individual element. All right, so here's the producer process. So we're going to wait until we can gain access to empty, wait until we can gain access to mutex. So mutex controls access to one dude there. Empty is going to start off an n, so at least initially we should definitely be able to grab something. The very first PCB there, let's say we have 10 buffers. Empty is 10. So we'll grab the resource, decrement to 9. No big deal. Mutex is also start off as 1, so whoever's first in line can get in there and decrement that to 0. So at the very least, after the original producer, whoever hits this first, he will definitely be able to get through these. Okay? And then we add the item to the buffer, so each of these can hold one thing. So we're going to now decrement the number of empties. Well, he's already been decremented, actually. And then we're going to, so if we had 10 queues, one of those queues has something. It's no longer an available bucket to put something into. So that got decremented, but never got re-incremented. So now that 10 has become a 9. But the mutual exclusive semaphore, which was controlling access to the group of buffers, let's say, it was decremented here, giving us only one process access to this producer, and then he was incremented right here. And then we also incremented the number of things that were full. Okay, so we're actually using a semaphore in this case, not necessarily to control access, but we're actually using it as a counter. But it's an atomic counter. All right, and we just keep doing this. This is the producer. So every single time somebody wants to add an item to the buffer, we make them wait in line for it. As long as we still have a place for them to put it, that's what empty says, we're going to let them in. And as long as nobody else is currently filling a buffer, we'll let them in. Okay, so that's kind of the producer side of this. Consumer side of this, well, we're going to wait for there to be something in a buffer. All right, so as long we have to wait till full is something greater than 0. Remember, full started off at 0. So the consumer, we can't consume something from a buffer until there is something in at least one of the buffers. Okay, so that's that part of it. Then again, we wait for it to be available. So notice we have the single semaphore, mutex, that is controlling access to the buffers in general by both the producers, the people filling the buffers, and the consumer, the people retrieving from the buffers. We're only going to let one person in there at a time. Whether that person's a producer or a consumer, they're competing for that same resource. They're just using the resource differently. Make sense? All right. So this guy goes in, he removes an item from a buffer, then he says, I'm done with the buffers, and then he changes the value of empty, increments it. Okay, because now there's one more empty spot for somebody, for a producer to store stuff in. Okay, and we keep doing this forever. All right, so kind of coming back to this, so the bounded buffer problem. Based on what we just talked about, what does this solution guarantee? What problem are we solving here with the bounded buffer problem? And what could we apply that to, kind of in real life stuff? Would we ever in this scenario allow somebody to get into the room to consume stuff when there are no elements in our buffers to consume? Can that happen in this scenario? Well, because we're protecting it with two separate, okay, we protect the room with one semaphore. Is the room available? The second semaphore is there stuff that you can actually retrieve from the room? So we guarantee that you can't get into the room unless there is a resource for you to consume. Similarly, on the producer side of things, we're controlling the room with the exact same semaphore, so we are controlling that room from both. That bouncer protects both, guards the room against producers and consumers. All right, VIPs and normal steerage alike. Okay? But at the same time, it's also not going to let a producer into that room if there isn't an available buffer to store whatever the producer wants to store. Okay, so we're using 3 semaphores in order to protect one resource from both producers and consumers. So we either A, never let somebody in to consume something that's not there, or B, never let somebody in to produce something when there's no room to put it. Okay, so that's the bounded buffer problem. The solution uses 3 semaphores to protect that. Each one is protecting an idea. The first one is the idea that this room can only be occupied by one person. Another one is the idea that a producer can only produce when there's an available bucket. The third idea is a consumer can only consume when there's something in at least one of the buckets. Okay? So that's the bounded buffer problem. ReaderWriter problem. A data set is shared among a number of concurrent processes. Oh yeah, I know this problem. Okay. So, we have a file. We've already used this file example, right? So we have a data file, and we have two different types of people that are interested in this file. We have readers of the file, and does it matter how many people open up a file for reading if they have no intention of writing to it? No, that doesn't matter, right? So we have, just like producers and consumers, we have consumers of our file who are reading it, but they don't actually remove anything from it. They don't modify it. Okay? Only read the data set. They do not perform any updates. Writers can both read and write. We certainly need to guard against that, because now that file can change, correct? So problem, allow multiple readers to read at the same time, but only allow a single writer to access the shared data at the same time, because what they can do is destructive. All right, so there's several variations in how readers and writers are treated. All involve some level of priority. All right, so here's again a three semaphore solution to this. So we have one semaphore who, this guy controls access to the writing room for this file. Okay, so we have a room that's for writing, and we only let one dude in there at a time. Okay. Similarly, we have a semaphore for whether the file's been written. All right, and then how many dudes are currently reading. So some of these are being used as counters, some of them are not. So here's the writer process. So we wait until we're allowed to write. Then we do our writing. Then we finish writing. One semaphore protects the writing room. Okay? So can we write? If yes, we can go in, we can make any changes, knowing full well that if this is a room, the person who decremented this semaphore, who's later going to relinquish it, increment that semaphore, is the only one who can possibly be writing right now. Okay? So that's what the WRT guy is used for. Here's the reader process. Well, we have to wait for the reading room to be available. And they started off that guy at 1. Okay, so we're going to wait for it to be available. We're going to increment our read count. Okay, if read count is currently equal to 1, we're going to wait for the writer to finish writing. So we're incrementing that read count prior to checking to see if we're the first reader. If we're the first reader and there's currently a writer, we're going to go ahead and wait for that writer to finish writing so that we get the current version of that file. Okay? Then what are we going to do? We're going to signal the mutual exclusion thing. Okay? So this protects, what does mutex do? It protects a new reader coming in when the file is currently being modified. That make sense? It's not preventing readers from getting into the system. We can have as many readers in the system as we want. Okay, we're not preventing readers, but we are kind of holding on to readers, like saying, wait a second, now you're allowed through while the writer finishes writing the file. So any new reader is getting the updated version of the file if there's currently a writer working on the file. Okay? Let's see. And then in here, we are reading. So we're doing our reading or whatever, but notice that right here we've protected reading. This is the sandwich for a reader. So a reader comes in, they increment the number of readers. So we're protecting who has access to read count. That way we don't have two guys who try to increment the same guy at the exact same period of time. This guarantees an accurate read count, because read count itself is not atomic. Now realistically you probably could. If you didn't have to do two things here, if you only were incrementing read count and you were not going to try to guarantee that a new reader gets the most up-to-date version of the file, you could just treat read count as a semaphore and just always signal it, always increment it. Okay? So if we're doing that, then read count is guaranteed to be accurate because only one dude can modify that resource at once. Okay? Now, having said that, we're actually protecting two actions. the counting of this, as well as waiting for a writer to finish writing, which could be a very long time depending on who the writer is. All right, so this is a wait. We're controlling this resource in these lines right here. Then reading is performed without any control. Okay, we're not when we're done reading, or while we're reading, we're not being locked out. We're not being controlled at all. Okay, we're not within the bounds of a semaphore there. Okay, but then when we're done reading, we're going to wait for us to be able to escape. All right, because the same semaphore is being used to protect new readers. And why do we need to do that? Because we have to protect the reduction, a modification to read count. Make sense? So read count goes up when a new reader comes in, read count goes down when a reader leaves. We want to make sure that that value stays accurate, and that's not an atomic. A plus plus or a minus minus is not an atomic move. All right, so we'll relinquish, so we grab the resource, which allows us to reduce read count by 1 because we're leaving the room. If read count is currently 0, we'll go ahead and allow somebody else to come in and write. So this blocks writers while there are currently readers, but it also blocks readers when there's somebody currently writing. Make sense? This guarantees that readers always see an up-to-date file, and it guarantees that writers cannot change a file while there's currently active readers. So it's protecting that system. So again, using 3 semaphores to pull this off. All right, so variations probably don't make that much difference here. All right, dining philosopher problem. Philosophers spend their time thinking and eating. Exactly. They do not interact with their neighbors. Occasionally, they try to pick up 2 chopsticks, one at a time, to eat from a bowl. All right, so they have chopsticks on either side. So here's our little picture. So here's our diners here. And left hand, right hand chopsticks. Okay, this chopstick is shared by the right hand of this guy and the left hand of this guy, so on and so forth. Okay, we're not allowed to take a bite unless we have 2 chopsticks. Okay? Otherwise, we've got to do the stab thing. Make sense? Do any of you go to Chinese restaurants and do the stab thing? Have you figured? Have you got the? It's a requirement for fat people. We have to be able to use chopsticks. Highly efficient. Huh? When you have 1 stick, so you don't have a squeeze move, you just have a stab move.
You do that if you have 2 and you also suck with chopsticks.
Yeah, then you can do that, but you can stab 2 things at once. Okay? Then you just resort to picking up your food. I don't get it. We go to these like traditional places, like these Chinese or Japanese restaurants, where they don't bring you a fork and stuff unless you ask, right? They bring you the chopsticks. My wife always asks for. I try to eat the soup with chopsticks. The traditionalist. I don't think Chinese people eat the soup with chopsticks. Okay. But I don't like the places that try to be traditional, but they bring you the normal spoon instead of the ninja spoon. Yeah, there's like there's a traditional Chinese spoon that's look kind of like a boat, right? It's like an upside down boat. Yeah, it's a ninja spoon. I think that's not technical. I don't think that's the technical name for that spoon. But yeah, so in any case, they need both of these chopsticks to eat, then they release both when they're done. So in the case of 5 philosophers, we have shared data. So we have a bowl of rice. That's our data set that we're dealing with here. Okay, and that for that bowl of rice, we're going to have a semaphore that relates to number of chopsticks. Okay, and this guy is going to be initialized to 1. Every single time we grab a chopstick, it's going to go up. Every time we try to grab a chopstick, it's going to go down. Every single time we put down a chopstick, it's going to go back up. There's an available chopstick now. Okay, but we do this with an array of semaphores. So we have a collection of semaphores, one governing each of these individual chopsticks. That make sense? All right. All right, so next class, we'll start off talking about the dining philosophers problem. I will probably give you a homework assignment dealing with dining philosophers problem on Wednesday. So we'll do that, and then on Friday we'll talk about the last bit stuff, and then we'll also talk about the final exam. Sound good? All right, I will see everybody on Wednesday.